Hello everyone. In this short video, we are going to look at equivalent systems and use of that in systems with distributed loads. And most of these pictures are taken from Engineering Mechanics Statics by Bedford and Fowler. So we say two systems are equivalent to each other if some of the forces in both systems are equal. And by the way, here bold font means they are vectors. And also some of the moments in both systems are the same for any arbitrary point P. So regardless of where you picked as point P, some of the moment in both systems about point P are the same, right? So this is the condition for equivalency of two systems. So if that's the case, then if you have system one where we have a bunch of forces and we have a bunch of couples of moments, we can replace all of those forces and all of those moments by one force and one moment, right? Where this force F is summation of all those individual forces. If that's the case, then this condition one is satisfied. And then for point P, if we put all of those forces F to pass through point P, now if you take some of the moment about point P in system one and system two, also you should get basically this scenario here. So in this system, if you look, some of the moments about point P in system one, which is coming from all of these forces and all of these moments, this is the same as this equivalent moment, because this equivalent force is passing through P. It has no moment for P. It's just this equivalent couple. So if I can find this equivalent couple to be equal to some of the moments of all these individual couples and individual forces in system one, and then this equivalent force to be some of all those forces, then guess what? I can say system one and system two are equivalent. So I can replace all of those forces and all of the moments with one force and one couple, and this is much easier to deal with than this one. So I picked this rather than this. It's much easier to deal with one force and one couple. And this is extremely useful when you're dealing with systems with distributed load. So systems with distributed load, they happen all the time. And in reality, I can say the only systems we have in nature are distributed loads. There is no concentrated load like this anywhere in the nature. Because when a force is exchanged between two surfaces, it's never applied at a single point. There is always a contact area. Right now, if you consider when I'm writing with my stylus on this tablet, you might say, well, look, here when you applied your pen to your tablet or computer, it seems like the force that you applied with the tip of the stylus is only applied to this small green point, right? But yeah, it is a small green point. If you look at it, it looks like a point, but if you had something to zoom, now you see it's not a point, it's actually a small surface. Okay, so if you zoom in, there is not really any basically local force or point force. Everything is applied on a surface. Now, sometimes this force, the surface over which the load is distributed is bigger. You can see it visually, right? So for instance, if you look at this beam and all of these sandbags that are on it, and this is how the sandbags are, basically some places there is more sandbags, some places less, then you can say this roughly, this loads, the weights of all these sands can be approximated by this kind of distributed load M force. And there is this load density omega or W of X, which is a function of location. So it's a curve, it's a function, right? And one simple case of that is a dam. You know, in a dam, as you go down, the pressure is equal to the pressure at the surface, P naught, plus the density of the fluid, in this case, let's say water, times G times H. And H starts from here and going down, so P is going to constantly go up as the depth goes up. And it's a linear manner with H, as you can see here. So if you look at the force on this vertical wall of the dam, it's a distributed load and it's linearly increasing. So they're all over the place, okay? Now, clearly you can consider this distributed load like a ton of individual loads. In theory, infinitely many of these individual loads, if you put them right next to each other, you can say this is a distributed load. So if I could replace all of these individual loads and couples with one single force and one single moment, can I do similar thing here for a distributed load? The answer is yes, you can. How? For that, you need to do some integration. So let's say here is any object that has a distributed load W of X, specific function with any shape, and you want to replace all of that with a single force. Where would you put it? Well, here, what I do is I come to location X, I consider a small length dx, and so the force equivalent for that small portion is going to be the W times dx, or W of X times dx. Why? Because this W is load per length. So if I want the load in that area, I have to multiply this W by the length of this element, which is dx. So this is the equivalent force that you have over there. So you can replace it with one single load, W of X dx. And this is just the load for that small portion. As you sweep this left and right to cover the entire region, you have to add all of these WX's together. And since you have infinitely many of them, instead of addition, you're going to be integrating. So integral of W of X dx is going to be your equivalent force. The single force is equivalent to all of these distributed load. Now, question is, where would you put it, right? You can put it anywhere from here, initial X, to this final X, let's say L. So where would you, between the range 0 to L, where would you put it? So I say I put it at location X bar such that the moment that this equivalent force is creating about origin is the same as the moment that all of this distributed load is creating about origin. If I say these two are equivalent, then my second condition is valid. Remember, so far I qualified the first condition, this equivalent big force, which is this much here. That force is, in terms of some of the forces in the y direction, is equivalent to the distributed. Now we have to make the moment equal about any arbitrary point. Which point is good? I pick the origin in this case because that's simpler. And so what is that? Well, this individual force here, W of X dx, what's the distance of it? What's the moment of it for origin? The distance of it is X. So I multiply Wx dx, this individual infinitesimal force, by this distance. That becomes a small moment. So small moment dm about origin is going to be this W of X dx, which is the force, times the X itself, times the distance. And I have to add all of these individual moments together. And again, since I have infinitely many, I have to integrate this, and that is exactly this guy here. That is total moments in the system on the left for origin. For the system on the right, it's just the equivalent force times the distance X bar. And if I say these two are equivalent, then X bar is going to be the integral of xw dx over f, and f itself is integral of w dx. And if you look at this, this is exactly the formula for a centroid. My previous video where I talked about centroid, this is exactly like a centroid, right? Okay, where the w at each location divided by the total effect of w, which is f, that's like the weight of that individual component. So where is X bar? It's closer to the places that have bigger W. So in this case, is that going to be right in the middle? No, because if you look at the right hand side of the middle, they have bigger W's compared to the left hand side. The area on the left hand side is smaller than the area on the right hand side. So I think that in this system, X bar should be a little bit to the right of the middle point, as opposed to exactly be on the middle or on the left side. Okay, so it should move a little bit to the right side. If it's uniform distribution, then of course it's exactly in the middle. Now let me ask you this. If it's a linear distribution like this, where do you think x bar is going to be? Based on what you learned in centroids, remember, look at this shape. This is a triangle. And if you remember, where was the centroid of triangle? There we go. You're right. If this total length is L, remember where the centroid was? It was what? There we go. L over 3 from this vertex or from this base. So if I have to replace this, let's say the maximum load here is W in this case. Okay, so W of X in this case is basically, and if you don't like to call it W, call it something else. So let me just call it something else. So I call it, I don't know, call it A. Okay, so this maximum here, density is A, the length over which is L. So W of X is clearly A times X over L, right? Where X is measured from this left side. Good. So if I have to replace that with an equivalent, clearly the equivalent is going to be 2/3 from this side and 1/3 from this side. And how much is it? Well, if you look at this formula, this is clearly the area under the curve of W, right? Look at that. That's the area under the W curve. So the area under W, that is your equivalent force. And clearly the area under a triangle is what? Is width times height divided by 2. So that force is going to be A times L over 2. And the location of it is exactly L over 3 from one side and 2L over 3 from the other side. That is for a linear load. As I said, if it's a uniform load, then it's very easy. It's exactly in the middle. So if this constant density is A and this length is L, if you have to replace it, then exactly it is going to be in the middle, and the value of it is the area under the rectangle, which is AL, and exactly it's L over 2, L over 2. So for simple scenarios, replacing a distributed load with a single load at a single location is extremely easy. But if it's this W is any other function other than constant or line, you have to use these two formulas, this one and this one, to find the equivalent load and the equivalent location, or the location of the equivalent load. Okay, now to practice that, let's look at this example here. So here we have a cantilevered beam on the right side, and the X is measured from here actually. And the load that you have is a parabola. So at X of 0, if you look at it, this is X of 0. At X of 0, this load is basically 3, right? The maximum is 3. As X goes toward 5 at this end, this term gets bigger and bigger. -1 is subtracted. So ultimately, when you come here, it goes to 0. So it's a basically backward or upside down parabola, right? So this is this quadratic function. The spread is 5 meters, and I want to replace that with a single load at a single location. Why do I need to do that? Because the problem did not ask for that. The problem says find the reactions at point A, and this is a cantilevered. So if I want to replace that beam, first thing I need to do is, if I want to draw the FBD on it, this is the FBD on that beam. So I have what here? I have a vertical reaction force, let's call it V. I have an axial reaction force P, and I have a bending moment M, right? Because it has 3 reactions. And of course, I have all of this basically parabola, all of this distributed load on it. So that's my FBD. Now, can I easily use some Fx, some Fy, some moment about this endpoint A and find MV and P? No. Why? Because this is a distributed load. So the first thing I need to do is to replace that distributed load by a single load, and then I can do it. So here, now in this case, P is clearly 0. Why? Because some of the F in the X direction is 0, but I'll write it anyways. That's fine. So you know what? Let me just include that. It's fine. It's not gonna hurt to just add it. So these are those three reactions that I have. This is V, this is M, this is P. Now I have to replace that with a single force F, which has this distance x bar. First, I have to do that. Now, this is very simple statics. So first is how much is F? We say F is the area under W. So in this case, it is the integral from 0 to 5, the total span. And the function is 3 times y minus x squared over 25. And then the x, right? So this is your W. And I bet everybody can calculate this one. So that is going to be x. And that is going to be x cubed over 75. And calculated at 5 and 0. Clearly at 0 it's 0. At 5 you are going to get this. So you are going to get 10. What's the unit here? Since this is kilonewton per meter, pay attention to the units. So this is going to be kilonewton. It's not Newton, that's kilonewton. So the equivalent force is 10 kilonewton. You can take all that distributed load and instead of it, you can replace a 10 kilonewton here. Now where? In which location? That's where you have to find the location. So you say x bar equals the integral of xw of x dx over the entire f. So this is going to be the integral from 0 to 5 of x times 3 1 minus x squared over 25 dx over 10. Okay, and again, I bet everybody can do this one as well. So that is 3x, so you're going to get 1.5x squared minus, you're going to get x cubed, so you're going to get x to the 4 over 100. There is a 3 here, so it's going to be 3x to the 4 over 100. And over this whole thing calculated at 5 and 0. Of course, at 0 it's 0 over 10, and you should be getting 1.875 meters. Okay, so this distance is 1.875 meters. Clearly it's less than 5, and clearly it's not in the middle. Remember, the middle is 2.5. It's on this side because this side has a bigger area than this side does. So it should be to the left of that and less than 2.5, which it is. So you see a sanity check says at least the number does not look wrong. So now that I have this system, all I need to do is to literally copy paste this elsewhere and solve for those unknown reactions. So there we go. This is your system now, and clearly some force in the x direction will tell you that the axial force is 0. Some force in the y direction will tell you that there is a negative 10 plus a v is 0. So v is 10 kilonewton. And some moments about point A, let's say counterclockwise positive, it doesn't really make any difference which direction you do it. And this is point A, by the way. Now, there is going to be a positive M and then positive F times X bar. That is 0. So from here, M is going to be negative F times X bar, and that is going to be negative 18.75 kilonewton meter. So these are your reactions: shear force, axial force, and bending moments. Done. So hopefully you see that what equivalent system are, where they're used for, and how to deal with distributed loads in different systems. Thank you so much. I'll see you in the next video.